Hey everyone, and welcome. Today we're going to pull back the curtain on something that's, well, at the very heart of computer science, data structures. Let's get right into it and see what really makes our digital world tick.
I mean, seriously, just think about it for a second. Your social media feed, your Spotify playlists, your photo gallery, it's all just data. So how in the world does your phone find that one specific song instantly without getting totally lost? Well, the secret is all in how that data is organized.
And this is the hero of our story. See, a data structure isn't the data itself. It's more like the shelf you put the books on, or the filing cabinet you put the documents in. It's the system, and it's all built for one simple reason: efficiency.
Okay, so this chart right here is basically our roadmap for this whole explainer. You can see that right at the very top, everything splits into two giant families. You've got your primitive types and your non-primitive types. Think of it like this. Primitives are the individual Lego bricks, and non-primitives are the cool, complex things you build with them.
So it makes sense to start with the Lego bricks, right? These are the absolute simplest building blocks, the basic ingredients that every other complex structure is made from.
And here they are. You've got integers for your whole numbers, floats for anything with a decimal point, characters for single letters and symbols, and finally, Booleans, which are just simple true or false switches. Believe it or not, every piece of data you interact with, no matter how complex, boils down to combinations of these four things.
Okay, so now that we have our ingredients, let's start cooking. This is where we get into the really powerful stuff, the complex structures that programmers design to handle much more sophisticated data.
And once we're in the non-primitive family, we hit another major fork in the road. On one side, you have linear structures, where data is laid out nice and neat, one thing after another. And on the other side, you have nonlinear, where things get a little wild and data can connect in all sorts of crazy ways, kind of like a spider web. We're going to tackle the linear path first. These are usually a bit easier to get your head around because they follow a really straightforward logic. One, then the next, then the next. Simple.
So the most basic linear structure is the array. It's pretty much just a numbered list of boxes all sitting right next to each other in the computer's memory. This makes them super fast for grabbing something if you know its exact address or its index. But here's the catch. If you want to add or remove something from the middle, you have to shift everything else, and that can be really slow. All right, next up is the stack. The best way to picture this is with a stack of plates. You can only put a new plate on top, right? And when you need a plate, you have to take one from the top. We call this last in, first out, or LIFO for short. It's perfect for any task that needs to be undone in reverse.
And this visual just nails it. See, we push 150 onto the stack. Then we push 250 on top of that. Now, to get anything out, we have to pop that 250 off first. And get this, your browser's back button, it works exactly like a stack.
Now, if a stack is like stacking plates, a queue is totally different. It's like standing in line at the grocery store. It works on the complete opposite idea. First in, first out, or FIFO. This is all about fairness and making sure things get handled in the order they arrived.
Yeah, it's just that simple. The first person in line is the first person to get served. In computer terms, the first piece of data that goes into the queue is the first one that gets processed. A print queue is a perfect example. The first document you hit print on is the first one that comes out of the printer.
All right, let's leave the neat and tidy lines behind. It's time to venture into the more, let's say, creative world of nonlinear structures. This is for all the data out there that just doesn't fit into a simple sequence, like, say, your network of friends on social media.
The two heavy hitters here are trees and graphs. A tree has a top-down hierarchical structure, just like a family tree or the folders on your computer. A graph is even more flexible. It's just a collection of points and the connections between them. This makes them perfect for modeling complex stuff like Google Maps finding you the best route or mapping out social networks.
So this table really is the perfect cheat sheet. Linear structures are simple, they're easy to implement, and they're great for sequential data. Nonlinear structures, a lot more complex to build, for sure, but they are incredibly powerful for modeling the messy, interconnected world we actually live in.
Okay, so after all of that, you might be thinking, so what? Why does any of this actually matter? Who cares how the data is organized? And it all comes back to our original definition, but I want you to focus on that last word, efficiently. Choosing the right data structure can be the difference between an app that feels instant and one that takes forever to load. It's all about speed and not wasting computer memory. It's everything.
So I'll leave you with a little challenge. The next time you use an app, any app,
whether you're searching for something, hitting the undo button, or getting directions. Just take a second and try to guess what's happening underneath. Can you picture the hidden structures, the arrays, stacks, or graphs that are making it all work so smoothly? Thanks so much for joining me.